Groundtracks are all about how bodies are moving with respect to the surface of the Earth, which is itself rotating. These animations aim to give a visual understanding of the differences between how orbits look in the Earth Centered Inertial frame versus the Earth Centered Earth Fixed frame, which rotates with the Earth. So the plot on the left shows this orbit in an inertial frame where the Earth is rotating, which is what you're used to seeing. But then the plot on the right is in the Earth Fixed frame, which shows what this Molniya orbit looks like from an observer's point of view standing on the surface of the Earth as it rotates. And then when you transform these Earth-centered, Earth-fixed vectors into latitude and longitude coordinates, you get a ground track plot like this, where in this specific example, you have this Molniya orbit that hovers over here by Russia and Alaska and hovers over here in the mainland Europe. So this is the 30th video in this series, and in this video I'm going to be introducing what ground tracks are. So start with what are ground tracks. They're basically latitude and longitude coordinates of your satellites or whatever body you're trying to observe with respect to the Earth's surface. So in here I have a few examples of what these look like. So the ISS here is in white, which looks like a sine wave because it's in a low Earth orbit, which this is what they look like when they're at that certain inclination. The polar orbits go up around the poles where their inclination is 90 degrees, so they look like that, where they come straight down through the Earth instead of more slanted like this ISS would. And again, this blue one is a Molniya orbit that has a very special property where it hovers over special pieces of land that you'd want to design in order to observe whatever place on Earth that you want to go to. And then this geostationary one is interesting, but it's actually just a point. It's this green one right here. And that's the whole point of these geosatellites, is that they're stationary with respect to the surface of the Earth, so their orbit matches the rotation of the Earth at zero inclination. So what are these ground tracks used for? They're very useful in orbit design. So you want to design what your orbit's going to be so you can have certain communications passes. So if you have some sort of ground station, you want to make sure your satellite's actually going to pass over it. There's also Earth observations. So if there's somewhere on the Earth that you want to observe, you want to make sure that your orbit is aligned such that you can do that. And then that's where sun-synchronous orbits are used, where you can go over a spot on the surface of the Earth every day at the exact same time. So if you want to observe over a year how, say, a city changes, you can do that because you're taking a picture at the exact same local time every day. And it's also useful for astronomy because you want to know where things are with respect to the surface of the Earth. Say you want to observe Jupiter with a telescope, you need to know when it's actually going to be visible to you wherever you are on the Earth. So, and how to actually do this algorithm, which I'll go over in the future videos, how to get into software. The first thing you have to do is you propagate the orbit in the inertial frame, which you're already used to doing here. Where the inertial frame is going to be the J2000 equatorial because you want to do it with respect to the surface of the Earth. And then after you're done with that, you want to rotate all the coordinates to the Earth-centered Earth-fixed frame, like the one I showed. So this is an example of the Earth-centered Earth-fixed frame, where actually the z-axes of the Earth-centered inertial and Earth-centered fixed are actually the same, and all that changes is that rotation of the z-axis. So you have at some point in time here, you have your x-axis, which points at 0 latitude and longitude, which is just south of Ghana here. You have it pointed in one direction, and then your y is going to be perpendicular to that, and it's rotating in that z-axis. So the way to do this in SPICE, there's a function called pxform, where you take the frame that you want to go to, the frame you're at right now, the frame you want to go to, and whatever timestamp, and it gives you a rotation matrix. So that's going to be from inertial J2000 to Earth-centered Earth-fixed. It's going to get that rotation matrix. And then after you have this rotation matrix, you transform your position vector of your satellite to the Earth-centered Earth-fixed. And then from there, you convert those rectangular coordinates, Rx, Ry, Rz, to spherical coordinates, which are the radial distance, latitude, and longitude. And then again, SPICE has a function for that. So it'll be pretty straightforward to plug into software. So that's it for this video. Make sure to give a like if you actually liked the video to help me out with the YouTube algorithm. In the next video, I'm going to go over how to start with plotting these Earth coastlines, so then you can be able to visualize the orbits you're making. So yeah, leave any questions in the comments, and thank you for watching.